you get introduced to Professor Abhijit?
Okay. Hello.
Okay, please start.
We'll start. A very good morning to all the esteemed dignitaries, distinguished guests and valued participants. I am Little Pradhan, a PhD student from the Department of EECE. I welcome you all to this 5-day GIAN program on modeling, control and operation of grid-connected green hydrogen energy system. The development of renewable, green and clean energy has gradually become an essential theme of the global energy technology revolution. Hydrogen is a crucial energy carrier and a vital component of the future energy system. Its advantages and potential application make it essential for energy transition and climate change challenges. Hydrogen energy, a secondary energy carrier, offers ease of storage, transportation and mobility, facilitating advance in industrial manufacturing and transport. IIT Dharwad is committed to create an academic campus having net zero in energy along with water and waste by 2030, which is in line with the objective of this course. I would like to introduce the esteemed dignitaries, distinguished guests present with us today. Professor Venkapaya R. Desai, Director of IIT Dharwad. He is also the Professor in the Civil and Infrastructure Engineering Science at Indian Institute of Technology, Dharwad. I would like to request Course Coordinator Professor Animesh Sahoo to felicitate Professor Desai with a bouquet of flowers. Okay, so I welcome all our guests to kindly light the lamp and provide best wishes to start the program.
लेडीज फर्स्ट, पहले आपको जलाएंगे. Maybe you need to write it again. और एक बार ठीक कर सकते हैं. You can take this speak. इसको right on top. नहीं ठीक है उसका आवश्यकता नहीं. ठीक है. दोनों मिलकर लीजिए. आप
would like to introduce the esteemed dignitaries, distinguished guests present with us today. Professor Venkapaya Ardesai, Director of IIT Dharwad. He is also the Professor in the Civil and Infrastructure Engineering Science at Indian Institute of Technology, Dharwad. I would like to request Course Coordinator Professor Animesh Sahoo to felicitate Professor Desai with a bouquet of flowers. Professor Jahangir Hossain from School of Electrical Engineering and Data Science, University of Technology, Sydney, Australia. He is our foreign expert for this 5-day GIAN program. I would like to request Professor Sahoo to present a bouquet of flowers to Professor Hossain. Professor Narayan S. Punnekar, Dean Academic Program and Professor. I would like to request Professor Sahoo to felicitate Professor Punnekar with a bouquet of flowers. Professor Pratyasa Bhui, Dean R&D and Associate Professor in the Department of EECE. I would like to request Professor Sahoo to present a bouquet of flowers to Professor Bhui. Professor Animesh Kumar Sahoo, Course Coordinator and Assistant Professor in the Department of EECE. I would like to request Mr. Tejaswi to present a bouquet of flowers to Professor Sahoo. Now, I would like to invite Professor Venkapaya Ardesai, Director IIT Dharwad, to share a few words.
Dhanyavad, that is thank you. Suprabhat, that is good morning. Swagatam, that is welcome to all the participants. The external participants, I was told that from industry there are 7 persons and from academia there are 18 persons. Plus of course the internal, does it include the internal people also? Yes. That is 18, okay, that is totally it is 25. Okay, so this GIAN program, the expansion is written there, I am sure all of you may be knowing. So here this is on hydrogen energy system, green hydrogen energy systems, modeling, control and operation of grid connected green hydrogen energy systems. So over the years, there is an emphasis on sustainable development, which in the Indian terminology is known as Akshaya Vikas. And within this as one, and we all know that energy is the 6th major requirement. Many times even it is 4th also, like say air, water, then roti, kapda, makan, that is food, that is clothing, shelter, and even many times, and the 6th is energy. But many times even energy is needed even to supply conditioned air. If it is too hot also we cannot manage, if it is too cold also we cannot sustain. So therefore there is an emphasis, energy is a need, but over the years many of these energy resources, they were not sustainable, like say fossil fuels. So they were resulting in more adverse impacts. That's why to overcome these, or to minimize, substantially minimize these adverse impacts of non-renewable, conventional, non-renewable, which are conventional energy sources. Now there is an emphasis globally on renewable energy sources. They such as solar energy, wind energy, then small hydropower, and of course this hydrogen energy, that is the green hydrogen energy. Of course, I am not an expert, so the thing is here we know that there are many systems known as hydrogen fuel cells, wherein the end product is water rather than a flue gas or something which may result in air pollution and other adverse hazards. So here that is and then through that energy, because I am basically a civil engineer, let me share my background. How many of you have seen Swadesh movie in Hindi? Please raise your hands. Okay. In fact, it is a strange coincidence that my PhD topic in Clemson University, South Carolina, USA, was exactly the topic in which this Swadesh movie was this one. A NASA scientist returns home to Bharatam, that is India, and then he is involved in rural electrification of a hilly village or a hilly gram, Parvatiya gram, and the turbine which that is one is the cross flow turbine, and in fact I had the distinction of working on 2 sponsored projects by what is known as the Bonneville Power Administration in Portland, Oregon in the northwest USA, whereas South Carolina is in the southeast USA, almost diagonal of across the mainland of US. Okay, so without taking much time, so I am sure we all need to do that is promote the renewable energy, and we are fortunate that Professor Jahangir Hossain from University of Technology, Sydney is the main resource person. Do you have other resource persons also? Okay. Okay, but anyway, he is anyway, this is a 5-day program, right? So therefore, I am sure by the end of this 5-day program, you will have more knowledge, and so eventually in whichever your engineering college or your industry, so there you will explore the possibility of implementing these. Maybe may not be in this one, even if you implement in a small way, that is a major achievement. Maybe take it as maybe in a matter of say 1 year or 1.5 year. Say after, so today we are in the middle of July. Say suppose by the end of say 2026, if you as an individual build a coherent team in your organization, whether it is an academic organization or an industry, and then by 2026 end, if you are able to show some measurable progress, if you can do substantially well, that is excellent. And in fact, other this one I was just inquiring about this one. So I was told by Professor Hossain that this hydrogen energy is a DC, direct current, and in fact we have a team led by Associate Professor Satish Banawat. I hope you will involve him also in whatever discussion, whatever it is. So therefore, these things, like say for example, we unnecessarily, that is the the direct current, if we go to the conventional alternating current, then again there will be conversion from DC to AC, then again from AC back to DC, and then so we may lose lot of energy. So even that actually, that aspect Professor Satish Banawat along with his foreign collaborators, I know an Indian chair professor of Indian origin in Clemson, Professor Rajendra Singh actually. So along with that they are working as one. So I hope you will take all the good things and then you will show measurable progress. You can call maybe Professor Sahoo or maybe our Dean R&D, that is Professor Pratyasha Bhoi, or Professor Abhijit Kshirsagar, or your Professor Satish Naik Banawat. And so eventually that is, say suppose after you attended just a 5-day program and then we have implemented in a matter of say 1 or 1.5 years, this is the measurable progress which you have achieved in our organization. If you can show that much, that is the real befitting swan, that is tribute to this small effort which is done under that is Professor Animesh Sahoo in his swan. So I wish all the best for this one, and again swagatam to this one. Whenever you get time, please visit the IIT Dharwad campus, and in fact this Saturday only we also have our graduation. Okay, so therefore all of you are hosted in the campus only, are staying in campus only. I think I was told that even Professor Jahangir Hossain was given a accommodation, was arranged accommodation elsewhere. Maybe there could be some, because of the overlap this one, there could be some maybe inability from our end to that is properly provide this one. So kindly apologize us for any this one, and I am sure you will take it positively. Dhanyavad. Thank you.
Thank you, sir. Now I would like to invite Professor Jahangir Hossain, foreign expert of the program, to share a few words.
Honorable Director, like all academics from IIT Dharwad, and most importantly, all the attendees, good morning to all of you. Actually, this is a very exciting time to, like, work in the energy sector. As you know, like, there are so many things happening in India, Australia, and elsewhere in the world. So you know that, like, the most country, including India, Australia, all are in the transition phase, moving from fossil fuel economy to clean energy economy. And to do that, I mean, definitely there are so many challenges as well as opportunities, I mean, for us as well. Now, like, in recent year, you see that, I mean, due to climate change, many countries, even I see like many in Australia, they are actually, experiencing most frequently like severe weather event, like, bushfire, flood, tornado, and so on. Some of the area, like, they are experiencing like flood, one in like 100 years, even one in like 1,000 years. So they haven't experienced severe weather even like this. Now, to address this, definitely, I mean, we have to move to, I mean, more like clean energy economy. So, I mean, in clean energy economy, you see like there are so many new technologies coming. As like the director mentioned that new, like, renewable energy generation like wind, solar, biomass, mini hydro, and so on. And number of like, energy storage technology like battery, hydrogen fuel cell, flywheel, and so on. And also other technology like, the electric vehicle, and so on. So what I'm trying to say that, I mean, all of this new technology is still, I mean, in the transition phase. Although there are many like commercial available, but still there are room for, further improvement in like, energy efficiency, like, energy management, control, optimization, and so on. Now, like in Australia, actually, we did number of survey to find out like that skill knowledge that actually we need to work in the future energy sector. And also all the existing workforce, maybe they are working for like, 20, 30 years in the energy sector, whatever the skill, I mean, they have already have it. So what we found out that there are actually considerable gap between the skill that we need to work in the future energy sector and also the skill they have. So what actually we need to do, either we need to, upskill the existing workforce, or, I mean, we want to have like, update our program like, either electrical, civil, mechanical, or other, I mean, engineers to have those skills so that they can contribute like in addressing the problem that actually all the humanity are facing in recent years. And as you know that, I mean, in coming years, also, I mean, it's not enough that you have skill only in certain area. Because the way the industry is, I mean, revolutionizing that all are actually interconnected. For example, if you see the electrical grid, previously people have just knowledge in like an electrical machine, transmission and distribution, but now it's not enough because the electrical sector is strongly coupled with other sector like electrified transportation like electric vehicles, and also like IT, sensors and so on. So what I'm trying to say that to contribute in the either industry academy in the next decade, we need to have definitely very deeper understanding whatever area you are specialized, but at the same time also you need to have knowledge like artificial intelligence and control, AI, sensor and so on. So again, hopefully although my expertise more on the electrical engineering, so although we are saying like the hydrogen, but we're going to focus more on the electrical side of hydrogen. I'm not expert actually in the chemistry, like chemical side of the fuel cell or even like electrolyzer. So we're going to be focused more on the electrical side, modeling, control, and the grid integration. So hope you're going to enjoy and we're going to learn from each other. So I'm not saying like I know everything about these topics. Maybe some of you like who are work in the industry, you might have better practical knowledge than I do. So we'll learn each other. So finally, I would like to thank Dr. Animesh to organize this event. I know like there are plenty of work that he has done. So hopefully, we're gonna spend time together and learn from each other. Thank you.
Thank you, sir. Now, I would like to invite Professor Narayan S. Punekar, Dean Academic Program, to share a few words.
Good morning to all the participants, and also welcome to our resource person from Australia. GIAN courses are very resource-intensive courses, and we have had a number of GIAN courses here already. What I understand is that it will be an intensive 1 week for you, hopefully good learning, and there will also be a certification at the end of it, right? Okay, so welcome to IIT Dharwad. Have a look around the campus as well. We have a beautiful campus, and also spend enough time to learn from each other. I hope you will have a good time. Welcome again. Yeah.
Thank you, sir. Now I would like to invite Professor Pratyasa Bhui, Dean R&D, to share a few words.
Good morning, everyone. So many thanks to Professor Animesh for arranging this course here, and also Professor Jahangir to visit IIT Dharwad and offering this course. So I'll just give a brief overview of research and development that is taking place at our institute. So you know that our institute started in 2016, so it's not a very old institute, just 9 years. So still we have done good progress in R&D. So we have almost 100 faculties, but half of them joined in just almost 2 years. And the number of projects has now increased to almost 140 and total funding of almost 65 crore. And also industries, private industries, they have donated generous amount of money, almost 10 crores. And also consultancy project we have received from different government and private organizations, almost 5 crores. Apart from external funding agencies, also our institute has invested lots of amount of money in infrastructure, R&D infrastructure. Institute has spent almost 150 crore in R&D labs to set up world-class, state-of-the-art lab facilities. So if you compare our lab facilities with any other institute in India, at least wherever, if you can compare similar labs, you will see almost all major equipment facilities we have. Even if you visit our power lab, you will see like real-time simulation facilities, all DC supplies, power amplifiers, all the important softwares like PSSE, PSCAD. So I'll suggest you also visit our labs, also send your students for collaborations. If you are from industry also, you can we can explore collaboration in these 5 days. Now, also you have signed almost 50 MOUs with different organizations, and 10 I think with foreign universities, and remaining are with Indian organizations. And also you have established a Section 8 non-profit company called Dharti that helps in providing funds, space and research infrastructure for science and technology related startups. And with 10 crore funding from BIRAC and also Finance Minister MP Srimati Nirmala Sitharaman. So we also have a center called BioNest to help biotechnology related startups. So already there are almost 10 to 15 startups are either incubated or in the discussion phase in the under Dharti. So now coming to the course, modeling and control of grid connected green hydrogen energy systems. When you talk about electrical grids, we know that now the time is for renewable energy. And at present, all the renewable energy that we are talking about, like solar or maybe wind, are mostly working as maximum power point tracking mode. So based on the weather conditions, whatever energy power is available, the renewable sources are injecting into the grid. But now also Indian grid, we know that we are planning to increase the renewable generation to 500 gigawatt. And if we increase renewable energy that much, so we know that at present they are not providing any ancillary services. Now all the ancillary services like frequency control, voltage control, they are being done by the conventional generators, thermal generators or hydro generators. But if we replace the thermal or hydro generators with renewables, and also renewables do not provide any services, then the grid will collapse. So now there is a possibility that you can still run the renewables at MPPT mode and provide the services from green hydrogen. So whenever you have extra generation from renewables, you can generate hydrogen, use it for long-term storage or for other applications. So it can work as, it can provide grid services, ancillary services. And at present, we do not have much green hydrogen facilities or generation in India, but as per the National Green Hydrogen Mission, it is going to change soon. So with this, I hope you will enjoy this course, and also you visit our campus and visit our labs, and whenever you get free time, you can also, we can also interact with faculty, students. Thank you all.
Thank you, sir. Now I would like to invite course coordinator Professor Animesh Sahoo to share a few words.
A very good morning and warm welcome to all the dignitaries, chief guest, our director, Professor Jahangir Hossain from UTS, our Dean Academic Program, Professor Punekar, and Dean R&D, Professor Bui, and all the valued participants. And thank you for coming to this small event. I can say it's 5 days program for this, I can say big topic like this grid connected green hydrogen energy system. But I can promise that may not be not full, but these 5 days will definitely put a foundation in all of you to explore more on this topic, which is emerging in the field of power and energy systems. And I hope all of you belongs to somehow electrical power system, power electronics. So definitely we'll link somehow to your basics to the upcoming research space which we are talking about. And I hope you enjoy these 5 days, enjoy the campus, enjoy the lectures, and enjoy interacting with everyone. Thank you. Welcome.
Thank you, sir. Now I would like to invite all the participants to introduce themselves briefly.
Name and organization, and then professional experience in number of years.
Okay.
Good morning, sir. I am Pratibha Hurkadli, working at KLE Technological University, Belgavi campus, and I have a teaching experience of 8 years.
Good morning. My name is Debraj Sarkar. I am from KLE Technology University, Belgavi campus. I've got around 10 years of KLE Technological University. Yes, sir.
Introduce.
Good morning, one and all. I am Dr. Tamalika Chaudhary from KLE Technological University, Belgaum campus. I have 9 years of teaching and research experience.
Good morning to all. Myself, Dr. Nalini Karchi, from KLE Technological University, Dr. M.S. Visheshgiri, Belgavi campus. I have teaching experience of more than 20 years. Thank you.
My name is Ritu Sagar. I am working as an engineering officer in Power System Division at CPRI. I have 1 year of working experience.
Namaskar everybody, my name is Abhiram. I am from CSE branch IIT Dharwad. Reason I joined this course was to get a good foundation in the upcoming technology. Thank you.
A very good morning to all of you. I am Dr. Meenal Saronke, faculty from KLE Technological University, BBB campus, Hubli. I am here with the campus from past 23 years. Thank you.
Good morning, sir. I, Dr. K. Bapai Naidu from Aditya University. I am coming from Andhra Pradesh, sir. I have 10 years of teaching experience.
Good morning, everyone. Myself, Satish Chauhan. I am an assistant professor from Parul University, Vadodara, Gujarat. I have more than 10 years experience in electrical engineering.
Good morning, everyone. I am Nishit Sahoo. I am also from Parul University. I have around 15 years of industrial and teaching experience together.
Good morning. This is Naveen Sam coming from Jyoti Engineering College, Thrissur, Kerala. I have 10 years of teaching experience.
Good morning, everybody. Myself, Ajit, Director of Solar and Energy Solutions Private Limited. This is a company we are providing renewable energy solutions. I have an industry experience of 18 years in various domains like power systems. Okay. Thank you.
We have another meeting at 11 o'clock, so that's why you apologize for not being able to respond.
Good morning, everyone. Myself, Aishwarya. I am from IIT Dharwad. I am doing MTech here. Thank you.
Good morning, everyone. Myself, Sri Gauri Chikmat, and I am electrical and electronic student studying in KLE Technological University, Belgavi campus.
Good morning, everyone. This is Somappa B from KLE Technological University, studying electrical and electronics engineering, 5th sem.
Good morning, everyone. My name is Parth Nakadi, and I am currently studying electrical and electronics in KLE Technological University, Belgavi campus.
Good morning everyone. Myself Dharampreet. I am third year BTech student in electrical engineering from NIT Hamirpur. Thank you.
Good morning, sir. My name is Satish Kumar, and I am also a third year BTech student in NIT Hamirpur.
My name is Abhijit Kshirsagar. I'm a faculty in electrical department here, and I work on power electronics, converters, and various aspects of renewable energy integration.
Sir Abhijit Kshirsagar, who is also assistant chair professor,
Cradle.
Cradle actually. Cradle assistant chair professor, Karnataka Renewable Energy Level.
Thank you everyone. Now I would like to extend my heartfelt thanks to our chief guest, esteemed dignitaries, dedicated volunteers and valued participants for their active participation and support. We look forward to this upcoming 5 days program. The first lecture will commence shortly. Thank you.
Animesh, should I start? And finish at 12 or? Okay. Okay, good morning and again welcome everyone. So in the first hour, we're going to give like a basic introduction to green hydrogen system, and also we're going to discuss some of their practical application, mainly targeting the electrical, power grid and also electric vehicles. So I'm not going to spend time on that because you already have seen this one. So hopefully, at the end of the course, you will have some basic understanding about the whole green hydrogen system, including electrolyzer, fuel cell, different inverter, converter, and also different topology of inverter, converter, some technique for designing control, and also some application like hydrogen based microgrid. How we can design and then optimize, and also we're going to give some demonstration in the tutorial using MATLAB, how we can design and analyze like the device level as well as system level performance as well. Now these are the total content of this subject. So we're going to start with introduction, and then we're going to go for the hydrogen technology, for example, electrolyzer and fuel cell. Then we're going to talk about inverter and converter, like DC to DC, DC to AC, and AC to DC as well. And then we're going to also talk about how we can control different inverter, converter, and also the system level as well. But among the inverter, we're going to also particular focus on grid following and grid forming inverter, because that these are the two emerging technology for interconnecting not only hydrogen but also other storage like battery energy storage system, but they're also thinking for connecting for renewable energy based as well. But so far most of the grid forming inverter, they have been used for with the battery energy storage system. But having said that, it can be also utilized for other technology as well. And then as I say, we're going to also talk about the microgrid level as well. And at then we're going to also talk about how this inverter converter technology can provide ancillary service to the grid, which is already having problem with both voltage, frequency, as well as sometime small signal and transient stability as well. And then we'll finish by explaining something on standard policy regulation on green hydrogen systems. Now these are the content I'm gonna cover. So just gonna talk one by one. So I'll start with background to climate change and so on. So in my previous talk I already mentioned that due to different human activities, so all countries having problem with greenhouse gas emission. Now here I'm just showing some statistics for Australia. So here you can see that only the agriculture sector, so the greenhouse gas emission have actually reduced significantly, but other sector, although they have reduced slightly, but still almost going on almost at the same level. So there are certain
reduction, but to get that 2050 target, we have to actually reduce that greenhouse gas emission, not only from electrical power sector, but also other sector like transport, agriculture, and also like education, and other sector as well. Now again, like in Australia, as I said, like that we have got target for by 2050 to go net zero. I think in India they have little bit behind Australia. They are targeting like probably now 2070. But if you see here in the right hand side, I think most country, European, so most European countries, they have got in between like 2040 and 2050. Now in Australia, although like as a country we have got 2050, but actually different state they have got different targets. I am from like New South Wales, so in 2030, and they have got a target by 35%, but definitely by 2050 it's gonna be like 100%. And other state, they have got different target to reduce their greenhouse gas emission by different percentages. Again, this is again I already mentioned, like for India, their target to go net zero by 2070, and here are some statistics probably you already know. And for greenhouse gas emission, you know that there are like mainly 3 types of emission, type 1, type 2 and type 3, but type 2 is mostly related to the electrical energy uses. So for electricity network, our target mainly to reduce the emission coming like type 2, which is mainly from generation, transmission and utilization of different renewable energy, different energy resources. Now, although like different sector contribute to for greenhouse gas emission, but as you know that the electrical power network, they are actually one of the major contributor for carbon dioxide or greenhouse gas emission. Now, it's not like that only if we go for 100% generation coming from renewables, we can address all of the challenges. So due to that energy transition, the different sector in power system, like including generation, transmission, distribution and even behind the meter, there are actually many things happening. For example, if you think about generation, so as you know that currently most of the existing centralized fossil fuel generator is being replaced with renewable sources. So the transmission sector, although like is comparatively intelligent than distribution, but still in the transmission sector also there are several changes happening. For example, in recent year, you will see like many phasor measurement unit for remote area monitoring as well as control as well. So in Australia, actually we do have number of phasor measurement unit that actually installed in transmission sector. And also in recent year, as you know that the power electronics, which is getting like almost one of the most important component of the whole power system. And in recent year in the transmission sector, you will see different power electronics control. For example, different fax devices like STATCOM, SVC and so on, but also you see grid following, grid forming inverter as well in the high voltage system as well. And in many cases like high voltage DC, although high voltage AC is the most common for energy transmission, but high voltage DC also getting popular for interconnecting offshore wind farm, and also to interconnect for long distance transmission, mainly in the Europe, where they are connecting different countries with the high voltage transmission. In Australia, we do have one high voltage DC, but other than most of them actually high voltage AC. But in recent years, actually the biggest change is happening in the distribution sector, because as you know, the distribution sector in many cases the manually controlled. You see, in many cases, if something happen in the distribution sector, if for example, let's say the transmission line is disconnected for some reason, then what we do? We call the transmission operator, they come and then manually fix the problem, and it takes sometime week, sometime more than a week, right? So that's why to make the grid a smart grid or intelligent grid, whatever we want to say, we need to make the distribution system automated and intelligent. So that's why in recent year you see the most of the research effort and also investment from different utility, government, they are focusing more on the distribution side. And as you see that most of the small size distributed generation like the rooftop PV or small size wind turbine, small size battery, all are connecting in the distribution sector. And also another new technology you might heard about, microgrid, which is also getting popular to supply power in the remote area and also improve resiliency to supply power in the critical load. For example, let's say a hospital, different important laboratory and so on. So that also connected in the distribution sector. You'll also find smart meter, which is also getting quite popular to get almost real time energy uses, the price that we are paying, and also if we have got different appliances in the home, university or so on, we can also see which appliances using how much energy and what money you're actually paying for what appliances. And that can actually help you even to reduce your electricity cost depending on your personal requirement, and that's actually getting quite popular. In Australia, in some state now they have almost 90% meter in the home, like the smart meter. In some other state 30-40%, but all the states now they are moving to have more smart meter. And then the new load that either hybrid or plug-in hybrid, they are also connected in the distribution sector, and the technology like the green hydrogen, which is we're going to talk, that might be in the distribution, but also a big size can be in the transmission as well. And also many things even happening behind the meter, like zero energy home, demand response, and also many things happening in the electricity market as well. Now you know that the hydrogen is not a new technology. It has been in many countries using for different applications for many years, but in recent year actually is getting momentum for mainly to address the issue, as I say, for climate change, and also to get that net zero target, to decarbonize the transportation as well as electrical sector as well. And the reason because it's getting popular because it has got very high energy density, and also it's quite lighter if you compare with other type of fuels, and there are not significant greenhouse gas emission if you produce hydrogen from renewable energy sources. And this one is just showing the total value chains from green hydrogen system. So although we're going to talk about mostly all of them, so it does involve production, and there are many methods that we utilize for production, and we're going to touch most of the methods like gasification, electrolysis, and then steam methane, gasification, although we're not going to focus more on the carbon capture, but with some of that blue and other hydrogen system, we do use carbon capture, because that type of hydrogen actually emits carbon. Then we're going to also talk a little bit about like combining gas and electricity network, and there are some research going on, like combining these two methods and then improving the combined network, and then it does involve storage, and hydrogen can be stored in different form, as the liquid, gas, and even solid form as well. It does involve different application in the transportation and local infrastructure as well, and then we do have already number of end user for heating, vehicle, and residential commercial application as well. Now, as this subject more on the grid connected, and this one is showing like how that green hydrogen system in different way actually is connected with the electricity network, and it does connected with the gas network as well. So what I'm trying to say that there's gas network, electricity network, and also the hydrogen, they are all interconnected. Now at some stage, we can actually optimize and improve the performance of individual system, but to get actually the better benefit, sometime we might need to have the combined model for the whole system, to optimize the and also benefit from the coupled system. Although sometime it's not that always you have to consider the combined model. For certain application might be you can just consider either device or part of the whole system. But as I said, if you want to have the whole value chain, then sometime you need to develop the model for the interconnected system as well. And if you combine that all system, it does actually have number of issues. It's not like the electrical, but it does involve like the environmentals, because it uses water, it does use land, and also as we are going for more cleaner, but it still there are some carbon emission as well. And the other factor also we need to consider the economic issue as well, because as you know that we could have very resilient and very energy efficient project, but at the end if it is not economically feasible, no government or industry gonna adopt either your design or your model. So at the end, whatever we do, although it has to be optimal energy efficient, but at the same time, although we need to show that it's economically feasible as well. So at some stage, we're going to talk about some of the economic parameter when we have the system level design as well. Now again, you might already know about this. Different types of hydrogen. I'm not going to spend more time on that. So you know that we already using most hydrogen either gray or blue. So the gray is mostly we are having from fossil fuel, using either coal gasification or steam methane reforming. And the next one is blue. Blue, the only difference with that one that we use carbon capture and storage. So whatever the carbon is emitting from this process, we use that technology to capture and store it, which making more cleaner than gray hydrogen. And finally, this is the most economic one, and I think in the next generation technology would be the green hydrogen, where we use the input energy from clean sources, and then we use the electrolysis process to generate green hydrogen, and it doesn't actually emit any significant carbon from this process. Now although I mean we have like later in the lecture more details about different process. I mean how we gonna produce hydrogen from different sources. But here I'm just gonna give like in a quick overview of different processes. So for example, that steam methane reforming, which is again I mean already utilized in different countries, and here we normally produce from like the natural gas. It has got comparatively higher temperature. It could be from 700 to like 1000 degree. Definitely I mean in the process of in the presence of the like a catalyst, and you know that all like electrolyzer, they do have electrolyzer, and we're going to talk about that later. So in steam methane reforming, I mean it does produce hydrogen, also some carbon monoxide as well, and even a small amount carbon dioxide as well. Now later I mean this carbon monoxide again I mean we reutilize to produce actually more hydrogen, and then again it does emit some carbon dioxide as well. And as I said, like this is so far is the most dominant hydrogen production method in different countries. The electrolysis, as I said, like we're gonna give more focus on this technology because it uses like mostly electricity to split water, and there is no burning process, so it doesn't emit any significant hydrogen. So it does produce hydrogen. I mean from water, hydrogen and oxygens. And there are I mean different types of electrolyzer we're going to talk about, but as you know that alkaline and PM, that's are the most two preferable one normally mostly used in the electrolysis process. And there are some thermochemical process also used. I mean that uses heat and chemical reaction, heat from sunlight, and then they release hydrogen from like different feedstock, fossil fuel, and also it could be from biomass as well. And also you might also know that the solar concentrator, even the nuclear reactor, that also can produce that needed I mean at very high temperature using the process to produce hydrogen. And also there are other method biological that also use like bacteria and algae that can be produce hydrogen from biological reaction as well. So again just is highlighting that I mean different path from renewable, solar, just like water is spilling, that's it could be produce hydrogen, and then using electrolysis, solar, hydrogen, geothermal, that also could be produce hydrogen, and then from nuclear, and also from fossil fuel and process also I mean we can produce hydrogen as well. So there are I mean different pathway, but in this course we're gonna more focus on the electricity using the electrolysis process. Although I mean it might be difficult to read, but it's just giving like some comparison using I mean different method. Mostly important parameter could be that efficiency that we are getting from different method, and also cost, considering the base cost like the current one is steam methane reforming. So compared to this one, how the cost for other methods, and which technology which are already matured and which are still going more research and development to improve the efficiency, safety, and so on. So now again I'm just gonna go quickly more details about that different method that we can use for hydrogen production. So steam reformation, I already mentioned that this is one of the most matured and commercially established process. Like people, I mean different industry, they are already using to produce ammonia, to refine petroleum, and in some cases, hydrogen energy system as well. Again, this is comparatively, I mean, among the existing commercially available method, one of the cheapest method. And again, I mean, we're going to talk about that there are mainly three component: anode, cathode, and electrolyzer. So there are some chemical reaction happening both anode and cathode, and here you can see that, I mean, from that methane gas using water, I mean, it does produce hydrogen, but also it produces some carbon monoxide as well. And again, using that carbon monoxide, we again use with water, and that can actually help to produce more hydrogen. But again, you can see that still it emits some carbon dioxide as well, and that's why I mean, we need some carbon capture if you want to make this hydrogen comparatively more cleaner. It has got some advantages. I already mentioned, like it more matured, relatively low production cost, comparatively higher efficiency, but it does have some limitation in terms of carbon dioxide emission. It relies on fossil fuel, mainly the natural gas, and also it need higher energy input required process, because the process is highly endothermic. There are number of applications. I already mentioned that ammonia, petroleum refining, methanol production. It can be used for fuel cell, I mean, if coupled with carbon capture and storage, and it has use because it can be used like a blue hydrogen when we are integrating with carbon capture and storage technology. And this is, like, as I said, like the our most optimal and also desired process in coming years to produce hydrogen from different renewable energy sources. So energy might come either from solar and wind, and using that electrolysis process, I mean, we can produce hydrogen, but at the same time also it's gonna produce some as a byproduct some water as well. I mean, for this one, this is more like scalable, flexible, and also it could be distributed for hydrogen production in any area you want. And this is again, I mean, we many times talks that it use energy from renewable energy sources. So if you compare with electrolysis and steam methane reforming, so the cost, again, I mean, this is one of the factor that this is again, I mean, relatively cheaper than electrolysis. It more matured, but it has got definitely higher emission, and for this method it's almost like zero when you're gonna use the input energy from renewable sources, and it uses mainly water, electricity, and that one uses like fossil fuel like the natural gas. So we already talked about that advance. I'm not gonna repeat that one. So still, I mean, if you think about the cost producing the electrolysis, like in Australia, we have got still like $5 to $8 per kg, but to make it comparable with other gases, it has to be like $2. So there are so many project research work going on, I mean, how we can reduce the price by reducing the price from like hydrogen technology, by reducing the price of input electricity, and also by improving the energy efficiency for the whole system. And not only that, also I mean, so far the production is only very micro scale. So if you can have production very macro level, that also gonna help to reduce the price. Hopefully, I mean, that might happen in next 5 to 10 years, and if it happens, then I mean green technology gonna be used for different industry like ammonia, methanol, steel, cement, even for different transportation applications, energy storage, and more importantly, it gonna be connecting in large scale with the grid to produce different support to reduce might be peak demand, to improve power quality, and also to provide ancillary service like to control voltage, frequency, and so on. Now the third methods, the gasifications. So that's again I mean thermochemical process that converts like energy available from coal, biomass, and water into syngas, which primarily consists of hydrogen, carbon monoxide, and then carbon dioxide, and also a small amount of methane and other gases as well. So that could be like different feedstock that can be utilized to produce hydrogen using this process, and it also operate very high temperature if you compare with like the previous one electrolyzer. Electrolyzer operate like very low temperature, and this method actually need controlled actually oxygen. And these are the like very simple chemical reactions that's happening in anode cathode, I mean to produce hydrogen. So again I mean this is quite well known, and I believe all of you already know about this. Again this one also have I mean different types of application to produce hydrogen, synthetic gas, ammonia, methanol, waste to energy production. And it does actually convert low value and waste material into usable energy. So that's one of the important advantages of this method. It has got higher efficiency if you compare it with the direct combustion, but it does have number of limitation as well, because it does involve capital intensive technology. It produces carbon dioxide unless we use carbon capture and storage technology. In terms of like the overall process is most complex, and we need to like have good control, I mean to control the overall process. And this is giving like again comparison among 3 methods, but I think we already talked about most of this. So in this case like both are quite matured and commercially available, although this one commercially available, but still I mean is growing. So maybe still I mean we need further improvement of all the fuel cells as well as electrolyzer technology that's currently available. The biological, that's another methods that utilize bacteria and algae I mean to generate hydrogen through that natural metabolic pathway. So using like the light from sun I mean and also water, I can actually convert that one to hydrogen and oxygens. These are the organisms that actually use. So this is also like could be one of the quite popular method in coming years. So the only challenge is that it has got oxygen sensitivity. That's actually limits some side the efficiency of the overall methods. So there are some indirect I mean biological methods as well that also have two step, that actually can produce hydrogen from biomass using the photosynthetic methods. So you can see that from glucose and water, using light and bacteria, it can actually produce hydrogen, although it does have some carbon as well. And also the dark fermentation, that's also another method could be utilized to produce hydrogen from glucose as well. That's we already talked many times, like what is green hydrogen, and what are the different application, and why actually we call this green. That's you already know about that one as well. We already talked about that that it does have anode, cathode, and this electrolysis membrane, and then like that input energy coming from renewable energy sources, and then in the cathode from water and input energy, it does actually produce hydrogen, and using that hydrogen ion and oxygen, it also from water actually it has got the oxygen, this hydrogen ion, and this hydrogen ion actually pass through the membrane to the cathode, and then using that hydrogen, it actually ion, it produces actually the final hydrogen. I'll also skip this slide because you already have it, you can just read later. That one also we already talked about that impact of different green hydrogen technology on different sector. For example, in environment, it does help to reduce greenhouse gas emission. It can have impact to improve air quality, and also it can produce solution that's number of the problem that actually had been introduced by large scale renewable energy integration. For example, in Sydney, is what happening in different state, like off peak time. For example, in the morning and afternoon, we have actually the additional renewable energy generation. And in many cases, what happened that, for example, if you have got rooftop PV and you are producing energy, so if you supply energy in the grid during the off peak time, so instead of grid actually providing money, they actually charge you, because what happening that they already have enough generation compared to the load demand, and when we are supplying additional energy to the grid, actually it producing more problem to the grid. So power quality, voltage and frequency issue. So that's why they actually have negative tariff. That whoever supplying additional energy during the off peak time, they are actually have pay back money to the actually grid operator. And hydrogen actually could be a very good solution, to resolve that issue, that during the off peak time, hydrogen can be utilized, that additional renewable energy can be utilized to produce hydrogen during that off peak time, and then it can be utilized again using that fuel cell again to produce electricity if needed. Although so far we are not producing any electricity from hydrogen, mostly it using for transportation, heating, cooling, and other industrial applications. Now, in Australia, we already have number of projects, some of them ongoing, but some of them is already actually producing green hydrogen as well. Now, one of the biggest project now happening in in Queensland, in Brisbane, where actually they are the government is spending almost $15 billion So they have got like a big suburb where we have got number of different industry, commercial and residential. So the whole area actually they're gonna supply different like heating, cooling and all the industry and different like transportation application. So they're gonna using hydrogen from that particular area. Not only that, we are also having number of renewable energy hub and renewable energy zone where we do have the option including hydrogen in those energy hub as well as renewable energy hub as well as renewable energy zone as well. And in New South Wales government now they are targeting number of like the offshore area, like there are 5 areas they have already targeted, and the work has already been done to have 5 hydrogen hub, and in those hydrogen hub they are also installing like offshore wind as well. Not only that, in different areas like also in Victoria, in New South Wales, there are already number of projects, some of them like under construction and some of them already producing actually green hydrogen as well. Now this is again there are some other project as well, but some of the project, for example this one organized by CSIRO. So this is more like research and for testing facility they have got. So most university, whatever research we are doing, if we don't have like infrastructure for practical implementation, actually the university and other industry who are doing like research and demonstration, they can actually go and doing experiment and validation with that research organization as well. And like in terms of transportation application, so in Australia already we have like 12 hydrogen refueling station, which is out of 12 I know like almost like 6 they are already operational, because in Australia we do have number of hydrogen powered small car, but that number is not that high. But in terms of like heavy vehicle like the buses, trucks, there are actually number of them in different states. They are already running and they can easily get that hydrogen fuel from those fuel station. And as you know that if those vehicle use like battery, mainly for heavy vehicle, they need very longer time to recharge the battery. Another option to have number of batteries, which make also the system like the overall it would be like bulky as well. So for those reason, for heavy vehicle, as you know that the hydrogen would be the best solution. But having said that, still there are some hydrogen car available in Australia as well. And as I said, like in most states that we already having hydrogen fuel station that's already operational. And also like in India also, like you have number of projects that's ongoing. And I know that India and Australian government, they have number of actually discussion and talk to work together in this sector, because we also have potential that maybe this country like they can export, not only utilize, but also they can export hydrogen to other countries as well. So I already mentioned like different application that battery already we are having different application as well, but also the green hydrogen that will have even like bigger application in grid, even in ships, steel industry, even like aviation is also like already number of unmanned air vehicle, that they are already using hydrogen also. And also like the different fertilizer industry and other chemical industry also, I mean, they might be using hydrogen in coming years. Now this is also I already mentioned, like that fuel cell application in heavy duty vehicles and long haul transportation as well. And this is the technology already available. Only the issue is the price. But as you know that, I mean, even both like the battery and hydrogen price, even like the battery price, actually they are coming down significantly. Like in every years, the battery price is going down by 15%. So almost like in 3 years, battery price is going down like 50%. And if that trend continue, I believe in like next 5 years, the price for like IC engine based car and battery vehicle car would be almost like quite similar. Although I mean hydrogen, it might take little bit longer, maybe 5 to 10 years, like to going down the price. But the way that I mean both the research development and going, and most like government, they are actually spending heavily in this sector. So we are quite hopeful that I mean this time definitely hydrogen gonna be like one of the dominant fuel, I mean in coming years. So yeah, I mean it's not only transportation but also in decarbonizing the different sector, because in many cases you will see that some of the industry might not be directly electrified. So in those cases, I mean to decarbonize that, hydrogen could be like one good alternative potential. So it also can be used, as I mentioned, like in oil and gas refinery sector as well. In different like chemical production, and also steel, cement production, methanol production. In those industry also, I mean in Australia, already one of the steel and cement production, they are already I mean using the green hydrogen to decarbonize the sector, because in Australia what happen in any industry, if they produce like green carbon dioxide beyond certain level, actually there is a penalty. So that's why most industry, they are also trying to have like different alternative option to reduce their greenhouse gas emission, and that's why they have already started to use like green and blue hydrogen using CCS, I mean to meet their target. And energy sector, as I said, like still I mean there are not any like large scale integration happening, but I mean if you want to have like 80%, 90% renewables, then definitely I mean we have to think beyond only battery, because the battery have got like capacity only maybe few hours. But if you want to have like very longer duration storage, then definitely I mean hydrogen gonna be like better solution. So in definitely I mean the energy sector, it is gonna be using to solve many of the problems that we're gonna discuss in coming lectures. In the heating, already in some of the area in Australia, that's already they are using green hydrogen for heating application. Food, already I mean many of the food industry, they are also in the process of thinking to utilizing hydrogen I mean for their food production as well. Many semiconductor manufacturing industry, they are also thinking to utilize hydrogen in coming years. And as I mentioned that that different countries, they have got like different forecasting like about their upcoming hydrogen consumption as well as hydrogen export. So in Australia, I mean, we have got, I mean, different scenario considering like, you know, business as usual, or like a step change, or, you know, gradual change. But whatever way, I mean, definitely the consumption of hydrogen gonna be significantly increased in Australia. But in Australia, actually, the main idea is not only the national consumption, but also to export hydrogen in countries like, you know, Japan, Germany, Korea, and it could be between India, Australia as well. In India also, I found that they have also some forecasting that in coming years, they are like, you know, hydrogen market gonna be increase significantly. The way that, I mean, different industry, government, they are investing. So it's not only government, I mean, the private sector, they are also, you know, coming in this market. So that's going to be helping, I mean, to significantly increase the hydrogen market as well. And also like in not only India, Australia, but, you know, USA, China, European countries. So if you see, like, if we consider like the worldwide scenario, you know, by 2040, 2050, the demand gonna be increased significantly. So definitely, I mean, it's like a growing technology, and as I said, this is also quite exciting, I mean, nowadays to working in this area, because as I said, most of the green hydrogen technology, they are not matured, and there are number of challenges. And when you have challenges, definitely there are, you know, several opportunities as well. So those are, I mean, you are thinking, although I mean, I'm going to talk about more about different challenges, mainly the research challenges in coming lectures. But those of you are thinking, I mean, to give more focus in this area, you can see that there is a quite significant challenge to address the intermittency. If you think about while hydrogen, different renewable energy, all are grid connected, because like when we have got, like in Australia already we have got around 40% coming from renewable, but in some state like Tasmania and South Australia, they have already have close to 100% coming from renewables. So there are, when you have got 100% renewable and they are intermittent and the output power are variable, in many cases they are already having issue with the power quality. And also there was a big blackout in South Australia when they have got a problem like fall right through with the wind turbine, because they are having like 50% power coming from wind. And what happened, like there was a transmission line disconnection due to such severe weather condition, and for some reason actually they did not actually activate the fall right through of the wind turbine. And what happened, as that fall right through was not active, so when there is a disturbance, like in a voltage frequency got outside and the whole wind farm was disconnected. And then what happened, like there is an interconnection between like South Australia and Victoria, and the interconnection, when the local generation significantly dropped, the power exporting from other countries, they exceeded the capacity of the transmission interconnection, and that's how the whole state was like blackout, and it took almost like week actually to solve that issue. So in that regard, although I mean already, I mean the fall right through capability already included many of the existing technology, but to address that overall intermittency, both like planning, operation, we still need more research and development work when mainly considering the system level. Although device level, we need to improve that electrolyzer fuel cell, but I think the most challenges is still in the system level. So grid stability, that also like a quite growing challenge, already like 20-30% renewable, but and in Australia already like 3-4 like real events already happened using that like even like 20-30%. So they actually monitored and see that in number of cases in 2-3 areas recently there was like a instability and blackout scenarios, and when they captured the data from PMU, they found that actually like that small signal stability coming from interaction between different inverter, converter and controller, because you know that when that inverter converter technology is coming from different manufacturer, they always design the controller based on their own modeling, and in many cases they actually did not share what actually they have inside. So when that different technology coming from different manufacturer, and in many cases actually their controllers are not coordinated with respect to controller available in other like devices. In many cases, sometimes during their like internal interaction between the controllers, they actually have like instability issue, like sometimes small signal, or sometimes could be like the voltage stability issues as well. The cost we already mentioned, like that's high cost. We need more research to reduce the price, and also that improving mainly that technology PM, because this has got probably more opportunity to utilize that technology, because it has got better performance and also very fast compared to other one, but also it needs more research to improve their efficiency, their lifetime, and also adaptability to work in different environment as well. Renewable energy and catalyst, as you saw, that this is like one of the major element for responsible for higher cost. So we need more research to find lower cost catalyst, and also that can provide better performance. But the people who are working in material science, probably they can contribute in that regards to improve their performance. There are also limitation in terms of infrastructure as well, because for hydrogen storage transportation, mostly like if you see all the existing infrastructure, they are either unavailable or even in many cases underdeveloped. So in Australia, they're thinking blending hydrogen as well as the existing pipeline, but still there are many challenges and it doesn't happen still. So they are still thinking, how can they do that? So if you also want to produce large scale hydrogen, we need very reliable and cost effective distribution network to supply hydrogen from production to the end user. Grid integration, that's I already mentioned. That's also we need better planning and management to ensure stability and reliability of the overall sector. But also safety, that is also another reason. Still many people they don't want to buy hydrogen car, because they said if there is an accident and if something happen, that might be very dangerous for the driver and as well as the passenger as well. So that public reception is still, that's a problem, but we need to work with different people to better explain about the technology, their advantages, and also the safety level as well. Because at the end, as an engineer, whatever we do, if it is not accepted by the community, it's never going to happen in the commercial level. So that's why as an educator, industry leader, we need to also work with the community to convey the real message to the industry as well. And as this is a new area, also we need new standard, mainly to interconnect with the grid, and also deploying in the different industry. So we need to improve all the like different like IC, IEEE, there are some standard, but we need to work more, to improve the standard as well. And also the different country have got different regulations. So sometimes also if you buy some technology from one country, sometimes you cannot directly use in other country because their regulation is different. So that's why different countries, they also need to work together to unify the regulations so that whatever technology happening in any country, they can use in other country as well. But also the other biggest challenge is the policy that's always developed by the politician, which is completely beyond our academic capability. So whatever we do, unless country have got a policy, it's not going to be employed in commercial level. So again, with that probably I'll stop now. So these are the probably things that we cover mainly from that introductory discussion. In coming lectures, whatever we covered, we're going to be having in detail discussion, but whatever we discuss, if you have got any comments, any quick question, or even any final thought, feel free to share. Thanks for your attention. Thank you. But anyway, it's very introductory. Even if you don't have question now, maybe when you're going to talk about details about all of this topic area, you might be having question. So if you have anything quick, we can discuss. Otherwise, we can also leave it for coming session as well.
So one of the questions that keeps coming up is that there are multiple pathways to green hydrogen, right? So it could be just electrolysis, it could be reforming with carbon capture or some other methods, or even as a byproduct of some other processes. Is there some standard on purity levels or the kind of hydrogen that is produced, or is it all completely fungible and you can take anything from anywhere and introduce? Is there
no, definitely. When I'm going to be actually talking more details about all those method and technology, there is actually requirement that some of them cases you need very pure hydrogen. If you don't have pure hydrogen, again talking either electrolyzer and fuel cell. One of the cases input, other cases output. But actually, that impurity can have significant impact on the deterioration of the and also the life cycle of the technology itself as well. So yes, definitely the impurity either in terms of input and output gonna have not impact on the lifetime of the device level itself, and also in many cases when you're gonna be having a real application, they also have standard that it has to be maybe pure by that percentage. So in that cases also we'll be having some limitation in some of the techniques that we're gonna utilize. But again at the end, the way that you're gonna be deciding that probably I want less costly, but you're gonna be compromising with the quality, then probably you're gonna use one method. But if your requirement, let's say I want very high standard pure, cost is not a major factor, that maybe you're gonna be go for very high standard technique, maybe electrolysis and other process. So
I agree with that. My only question was actually, is there a way or is there a potential to match these sources or requirements today? Because my understanding is that some industrial process like steel, for example, right now they depend a lot on coal, if you were to simply use hydrogen instead of the coal, first of
Yeah.
all, you eliminate the carbon from coal completely.
Yeah.
You don't have to struggle so much. And then the hydrogen is, I think, from a process point of view, it's slightly better. But there, I don't think that you need very high purity hydrogen, because you don't really care that much about
That's
hydrogen impurities. So my question is, if there's a if there's an electrolyzer or something that is essentially doing renewable to not very pure hydrogen, can we then have it directly piped to, let's say, a steel industry or cement industry where you use it for reduction, and then don't care too much about purity, versus having to struggle with, okay, now I want to change it back to energy, for which I need good purity, otherwise my fuel cell will degrade, or I want to use it for transportation where maybe safety and again you have to compress it, all those problems are there. So do you see that there is some roadmap over the next whatever, maybe say 10, 15, 20 years, where these things can be matched to each other? Let's say low cost mass scale solar, where I don't even care about efficiency, right? So let's say I have in the outback you can put acres of solar, and solar cost is already down in cents and whatever. So let's say I don't care about solar cost, I have enough space, and just use it for something that it can be used for. So is there some matching that you see, or do you think that there's still some piece that is missing, that something can't be matched to everything else?
I think that's a very good question. I mean, what happened like in perspective of Australia, like in the previous government, because they were not only like very biased among like the electrolysis process, so they actually invested a lot to see like how actually they can improve that existing mature technology that's we already talked about. So they tried to see like whether that's gray, blue hydrogen producing using different method even can be utilized with the CCS to get their target. And they are actually that time they are having number of projects actually to see that not only using the single technology, but what about that we use like a mix of all that available technology, and then finding a unified way that somehow we can combine all together and utilize. But what happened like when the government changed and then the current government came, and they come up with their issue that they're gonna be heavily investing in the mainly the renewable and electrolysis process. Then now the momentum has little bit shifted, and they are more biased now to going for that only electrolysis process. But having said that, in Australia I did not see anything like combined effort from industry, government, academia to see the issue that you mentioned, to make it reality. But I think still there are some research, industry work still going on that other pathway as well. So I believe it's still not actually happening in the unified level, but it might happen at certain stage, because I think still we believe that we need actually mix of solution, not like a particular single solution that can solve our all problems. Yeah. Maybe have like 5 minutes, and then we're gonna.
So thank you, Professor. So we'll have now 5 minutes break, and we'll start the lecture 2. Thank you.
I'll open it.
from the introduction page and
Yeah. Okay, thanks for your time.
I will join you in the afternoon.
Okay, no, thank you. No. Yeah, I do understand.
So we'll start in 5 minutes only, so please be back. Why it is off, I don't understand.
I don't know, there are so many.
Can you leave this and open this and again close?
Hmm?
Can you remove this and again close? Some disconnection. Can again put?
No. But where did he save that one? Otherwise, I have to reconnect my USB.
Here's the starting page. You can presentation. Okay. So we are going to start the lecture 2, which is basically about the fuel cell basics, principles, components, types, advantage and disadvantage. I will hand over to Professor Hossain now.
Like, about fuel cell, but the next one, we're going to be talking more about the fuel cell modeling. And then in the tutorial using MATLAB, we're going to be talking about how we can, model fuel cell into doing different analysis. Now, there might be again some repetition, but I'll just skip if there is a repetition, because we already talked about, some of that electrolyzer fuel cell basics in the previous talk. So these are the topics we're going to be covering, but as I said that some of them I have already talked about. So although we talked about green hydrogen, that using electrolysis process we can actually produce green hydrogen, but if we want to use again electricity from green hydrogen, then the technology that we use, that is actually called the fuel cell, and fuel cell converts the chemical energy available in the hydrogen to electrical energy. You know that normally we produce electricity from sometime electromechanical, converting mechanical energy to electrical energy, for example, things like wind turbine. So wind turbine, we convert energy available in the wind to mechanical, and then from mechanical to electrical. But here, like photovoltaic system, so the energy conversion process is like electrochemical, from chemical to electrical. Now again you might already know about fuel cell. So fuel cell have got mainly three major part, that anode, cathode, and then electrolyte. And later we're going to be talking about that whatever type of fuel cell we mention, that's actually depend on what type of electrolyte actually we utilize inside the fuel cell. So what actually happening here, that in the anode there is the input like hydrogen, we apply oxygen through that cathode, and what is happening that using that electrochemical process, so the what hydrogen is coming here, that is actually split into proton, and then we have got free electron, and this proton that we are splitting from that hydrogen, it goes to the cathode through that electrolyter. And what is happening after coming here, that proton and that oxygen and electron, that actually again producing water, but that free electron coming from hydrogen, when it passes through that external electrical circuit, that is actually electrical energy. The process actually quite simple. The way that actually it generate electricity from that input hydrogen and oxygen. Now we here just talking about the fuel cell, but if you talk about the whole system, it's more than only like the fuel cell, which we're gonna be talking about later. So it does have other parts with the in the overall system. Now before going details about that, again fuel cell also have got different application. We already mentioned like the transport. It could be car, bus, truck, train, ships, aircraft. You might have different stationary application as well, like if you want to have a backup power supply system, It could be for a laboratory, it could be for a small community, it could be houses, it could be hospital, it could be university campus and so on. And there it also sometimes used with combined heat and power plant as well. It can be used for portable power supply for the portable devices, and one of the applications they are seriously thinking about the military equipment for applying like fuel cell application, and also it has a potential for space exploration as well. So there is a one industry space, you might know that Apollo, they are already actually using fuel cell for their space applications. And this is a little bit like history. Again, you might know that it started 1960 with that the first generation alkyne fuel cell. Then after that, we have like number of research and development to improve their performance, and in 1970, 80, 90, and even after 2000. So there are many things happening to improve their overall power rating, to improve their efficiency, to even improve anode, cathode, and also the electrolyzer, electrolysis process inside the fuel cell as well. Now, in terms of the important features of fuel cell, like if we just compare that whatever energy we are getting from like other chemical sources, for example petrol, natural gas, using combustion, steam turbine, and then generating electricity from that, you're going to get maximum like 30-35 efficiency. But if you just use like the fuel cell, and if you combine that CSP, like the thermal energy that we are getting, if you utilize that energy, then overall efficiency could be around 80%. But only like if you don't use that thermal energy, then it's going to be like a 40 to 60%. But it's still, you see that it's much more efficient than if you just compare like the conventional power generation that's coming from like chemical energy. Other features like as I say like that, there are number of efforts that currently going on just to develop that ion exchange member electrolytes that I mentioned in the previous, with much more efficiency and longer lifetime with minimum cost. So if actually that can happen, then definitely the overall hydrogen price is going to be reducing significantly. And these are the some of the like expected lifetime duration for fuel cell that being used like heavy duty vehicles. We are expecting minimum like 8,000 hours, 30,000 for like heavy duty truck, and 80,000 for like that's going to be utilizing for grid application, distributed power system. That's I already mentioned the efficiency, and definitely this is environment friendly as well. There are number of advantages if you compare with even like the combustion process that we mentioned, that you can produce electrical energy, and even if sometime if you compare with its other competitor battery, it also have got some advantages as well. Definitely, it can actually have longer operating times compared to battery. It can operate wider temperature ranges. Sometimes battery, its lifetime actually reduced significantly. It actually operate in very cold and very hot weather. And also this is efficiency, as already mentioned, is silent and it doesn't have any the rotating parts. It needs less maintenance. So these are the some of that advantage compared to combustion engine, or even like compared to battery as well. But again, like still there are some challenges as well. So this technology need like a constant fuel supply. It's still quite expensive, and it does produce DC. So as you know that we mostly use AC in our home, so we need like inverter, converter, technology with the fuel cell. If you want to have power supply in the AC load. And also like in terms of transportation application, it is heavily limited by lack of facility for hydrogen storage and distribution, that we already mentioned. There are so many technology now already available in the market as a fuel cell, but as I said that most commonly you will find alkyne. We also have like for phosphoric acid fuel cell, we have molten carbonate fuel cell, polymer fuel cell, and also the solid oxide fuel cell as well. Now if you see here, all of them have like different temperature range, but if you see that PEM, which use like polymetric as like electrolyte, that has very minimum like temperature. It's like around 80 degree centigrade. But the other than that, the other one have got comparatively higher operating temperature. For example, you see that molten, it is comparatively very high temperature. In terms of like efficiency, still this is without using heat, but as I say that if we use heat, then this efficiency gonna be much more like higher. And also like for power plant and vehicle application, we need higher capacity, which is PM electrolyzer has. So other one, the solid oxide, that also like have comparatively a higher capacity as well. But so far this is the one most people are giving more attention for the PEM technology. Now again, it will, like I'm gonna don't repeat it, the same principle, but only difference here. You can see that it does have anode, cathode, where we have got hydrogen and oxygen input. Only difference here that we use like potassium hydroxide as electrolyte. And what is happening here in anode, like in anode reaction from hydrogen, by splitting hydrogen we are having that's initially happening from oxygen. So from oxygen and water, and then whatever electron we are getting, using that one we are producing oxide ion, and this oxide ion passes to the anode via this electrolyte, and then at the end at the cathode using using that it actually produce at the anode side using that oxide and using that hydrogen coming as input. Finally we produce free electron, and this free electron again that is actually flowing through external circuit, which is again nothing but the electricity. And overall you will also get water as a byproduct as well. Now again this technology in general, that's like the summary. So So again, I mean, for this one, as we were talking previously, actually it needs actually pure hydrogen as an input. So other things, I mean, we already have discussed, and it does have got already some application. The space program that I mentioned, Apollo, they actually use this technology for electrical power supply as well as for drinking water for that space shuttle as well. It also have got the military application for having like portable power in very controlled environment, which is carbon free, and it does have application in some other industry as well. Again, I mean, if you want to have very details about comparison like in terms of efficiency and disadvantages is giving here. So later, I mean, when you have got time, you can also read. But again, this is again said like that this is one of the highest electrical efficiency among fuel cell, which convert chemical to electric very efficiently. It can actually operate with number of relatively inexpensive catalysts like nickel, silver, metal. So if you compare with PEM, which I mentioned, which actually need actually very expensive electrolyte, and that use actually platinum. You know, the platinum is a very expensive material. So as it use like less expensive, it has got lower catalyst cost if you compare with other one. Relatively fast startup because temperature is not that high, because when you have got very high temperature, you need relatively higher time for starting the whole system. So in some cases, if you need electrical power supply with very short period of time, then those electrolyzer which have got very higher operating temperature, I mean, that might not be like a best like electrolyzer for having quick power supply. But one of the problem for this one that this is quite sensitive to have like carbon dioxide, because if you have carbon dioxide either from air that's coming, or if you have got impure hydrogen, that's I mentioned previously, it actually reacts with the alkaline electrolyte to form actually carbonate, and this carbonate actually within that electrolyzer it does block that reaction site, and it's contribute to degrade the performance, and ultimately it actually reduce the lifetime significantly. So it does need like pure input, I mean, for this type of technology. And compared to PMC, also it have got lower power density. It also need, I mean, that carbon dioxide I mentioned, like it needs better management for carbon dioxide management, and also like that other liquid handling process inside the device, that also increases the overall complexity and the auxiliary system requirement. Then again, I'm just quickly go only again, I mean, you see that similar process, but the difference again, I mean, the electrolyte. So here you see that we using like the phosphoric acid as a electrolyte, that to convert chemical energy from fuel to electrical energy. Again, that from same process like from hydrogen, you are having proton, electron, and then a proton passes to the cathode through that electrolyte and combine with hydrogen, oxygen, and produce water, and the free electron is coming from here that produce electricity. So the process, chemical reaction, all are same. So the only difference would be again, in terms of efficiency, in terms of tolerance to carbon impurity. I think this one have got better tolerance than the previous one, and combined efficiency also quite better messier technology already available, but the temperature is little bit higher than the previous one, so that's why it had got slow startup time, and also the efficiency comparatively lower than PEMC. Next one, the molten carbonate fuel cell. Again, the difference here that it operates very higher temperature, and we use the molten carbonate salt like in the electrolyte, but again the process is quite similar. From like the cathode, we have carbonate ion which passes here, and then whatever it's combined with the hydrogen, and then it produces free electron, and that free electron is nothing but the electricity. It also have got many application. Some of the common that it can be used distributed CSP plant, waste to energy or biogas power system, and with CCSP as well, because it does have some carbon as well. Again, with all the same parameter, but it's just some comparison, efficiency, tolerance to carbon and so on. So again, I'll just leave this one. You can read in your free times. So this is the one that I was talking about, proton exchange membrane. And many of you, like if you are working in this sector, you might be working with this technology. So it uses like polymer electrolyzer membrane, it uses solid polymer membrane as electrolyze, which is again, as I mentioned, is quite expensive material, and that's the reason it's expensive, but it actually much faster than the PM. So in case of providing that ancillary service, as I mentioned previously, we'll show later, but actually this one provides much better performance than the first generation fuel cell. So again, the process all are same. We have the same input, but only difference the electrolyte. So again, from the hydrogen split, we have got proton and electron. This proton is passing to the anode, producing water, and the free electron is just like the electricity. So it has got comparatively low temperature, 67 to 80 degrees centigrade. It use it need a pure hydrogen with actually very strict requirement for like the carbon dioxide, and as I said, it also have got many application as well. Again, I'll leave this one to read for your free time in terms of doing advantage and disadvantage, because this is quite important, because when you're going to select that which technology I'm going to use for a particular application, then if you have knowledge that comparative analysis between them, then you can find out that which one might be best application for particular application that you might be working. So this is also something that's number of research work is going on. That also use high temperature, but here they use ceramic solid oxide here as a electrolyte, but in terms of principle is quite same chemical reaction that actually produce hydrogen. Only difference again would be that how it is tolerant to impurity, is efficiency, again the cost, and also the the operating temperature as well. And it's given again all the key features and also different application. So only things, as I said, that you see this has got very higher temperature, but also it can use different fuel as a input. So it has got quite flexible in the input side as well. Again, I'll leave. I'll not read this one, because it's just like different facts about advantage disadvantages, and it has got very slow start and shutdown time, considering that the temperature range, but it also got good efficiency and fuel flexibility as well, which is quite important when you're gonna think about for different application. Now we just talk about like fuel cell, but what about if you think about the fuel cell, the whole system? So the whole system actually had got number of subsystem. We already talked about oxygen supply and hydrogen supply in anode and cathode, but that's not only the fuel cell system. You need like the heat management, because you see that different one operates in different temperature. So we need a very good heat management system, and also it involves water. So we need also water management system, and we also need like power conditioning, for its better performance and longer life. And not only that, we also need like different sometime monitoring, sensor and control to improve that overall performance of the fuel cell system. Now that we just mentioned like fuel oxygen input, but that oxygen is not like that, it's just directly putting oxygen. For oxygen input, we use a system like that, which has got number of subsystems. So for example, that we use like air filter to remove any impurity you might have in the input fuel. Then we have also like the compressor, which is powered by which is motor, like just to pressure and deliver air and control flow rate to the fuel cell stack. We also have humidifier, which actually you need to maintain hydration and also prevent any performance loss. And then some of them also have like heat exchanger, just to preheat incoming air that's coming from waste heat from the system, like to improve the overall efficiency. We also need like flow control valve sensor, although it is not shown here, but as I said that if you want to remotely monitor control, then we need that different sensor and remote monitoring and also control system for optimal operation of the whole system. And also it does include cathode exhaust system, just to manage removal of excess air, water vapor and also the heat. And it can be integrated with the thermal recovery, for water recycling process as well. So this is the way that we use oxygen input to the overall fuel cell system, and same like that one for the hydrogen supply. We don't directly put hydrogen in the fuel cell. We use a system like that, where you might have hydrogen in the hydrogen tank as a storage. It either liquid or it could be gaseous form. Then we do have regulator, which can be used to reduce or increase the pressure to might be suitable for your fuel cell application, depending on what type of fuel cell actually you are using, and it can maintain like stable operating pressure. You see like that if you use like high pressure tank, that might be the pressure, liquid that might be in a different form, in different temperature, and also the solid. But anyway use can be using like a system like this, as a part of hydrogen supplying to the fuel cell. It also have got some other devices like monitoring, control, and sometimes we also use like that hydrogen recirculation pump. Some of them unused. You might again use like the feedback loop to put it back and use it to improve the overall efficiency. We also have like shut off valves and safety device. For the protection of like for the whole system during like unwanted situation. And then as does involve water and heat, so we need like water and heat management system, either to improve the performance, durability and the safety of the fuel cell system. And once you have that management system, it's gonna be like having like the temperature regulation and also the water balance, which might be critical for different types of fuel cell. And one of them, the critical one, that one, it does need actually very specified temperature and water balance to operate. And not only this one, the other one also you mentioned, it does need like water and heat management system. So this is like you see that we have got heat exchanger, water tank, water pump. So for all this to operate, actually we need that particular management system. And this one actually showing like the heat, and the previous showing like the water. Now these are the like main component for water and heat management system, and you see like all of them has got particular function. For example, like the coolant pump, temperature sensor, water separator, radiator, coolant loop, dehumidifier, humidifier, all of them have got particular function in the water and particular heat management system. Now later when we're going to talk about more detail about the modeling, in some of the application you see that we model all of them. In some cases, for certain application we neglect some of the modeling. But what I'm trying to say that at least you need to have good idea about that total fuel cell system, like what are the different component, what are their function, and then how we can develop that management system for the overall system. Now later I'm going to talk about more of the total modeling, but these are the like simple flow rate for the coolant normally used for that water and heat management system. So I'm not going to talk about more detail about the mathematics, because I'm going to talk about that one later. And this is like more about that water system, water balance, that water in and also the water out for the whole system, and using the balance we can develop that differential algebraic equation if you want to do modeling and simulation for different purposes, that I'm going to talk about the next lecture. So this again that that's I mentioned that water balance, it does actually depend on the oxygen flow rate, it does depend on the operating temperature, different pressure, stack outlet pressure, ambient temperature, pressure, relative humidity, all of them gonna come into the picture if you want to have very detailed physical model of the whole fuel cell system. And it's not only that, even if you want to integrate with the grid, and if you want to supply power for the particular application, we do need inverter and converter, and we're going to also talk about that DC to DC and DC to AC inverter later, but you know that all of them have got different functionality. It's not only converting from DC to DC, but that's one of the function. It can step up or step down, but also we do apply MPPT, that for like solar system and even for fuel cell. We need that control to make sure that whatever operating condition changes, any condition, we are getting maximum power, and that's control implemented in this DC to DC converter. And then finally inverter, it does invert from DC to AC, but if you want to apply different active reactive power control, that also we're going to be discussing in coming lecture. That can be done in the inverter. So again, I mean it does involve number of devices when we're going to talk about the whole fuel cell system for modeling analysis. I mean, in many cases we need to model all of them. In some cases we can use some of them, neglect some of them. So here you see number of them, like inverter, I mean converter we can use, but we're going to also have one session on different buck, boost and other type of inverter for stepping down, stepping up, regulating DC voltage and so on. And all of them have have got certain typical use as well. And then for inverter also we have got, I mean, different types of inverter, considering like the stage you might have single or two stage, depending on like grid connection. You can have like either like a voltage source or current source. And also in recent year that the multi-level inverter is also getting quite popular. So it could be like a multi-level converter also got different topology, like it could be like neutral point clamp NPC, cascaded Hayes bridge, flying capacitor, and so on. But again, I mean this DC inverter, it does convert from regulated DC to AC, but also it has got other function like that. If you want to get connected, then you have to synchronize with the frequency. So it's gonna be like either 50 Hz or 60 Hz depending on which country. If it is like Australia, India, I believe 50 Hz, but if you go like Japan, USA, 60 Hz. And also like whatever the voltage level, that has to be synchronized as well. And also it does involve the protection as well, like over voltage in many cases, isolating detection and so on. So as an inverter, but it's not only inverting from DC to AC, it does involve number of other control and protection, and depending on your research and project, I mean at the end you're gonna be using like whatever the model and simulation you need. And the other one also, like as I said, we're going to be talking about grid forming and grid following, and this is mainly based on like the grid connection strategy. So if it is grid connected, then we normally use grid following. If it is like it can be used like in grid connected, but mostly when you have got like weak grid or off grid, then normally we use like the grid forming inverter because it has got very good control capability. Even in many cases they have shown that like it's almost like a synchronous generator, which that the technology which is providing most of the control function now in the current grid, like voltage, frequency and other control through like an exciter, and in some cases in other fax devices. But in grid forming, I mean it has got actually capability to provide most of the control function that is being actually supplied by synchronous generator. And again, both of them had got different control. You might already know about some or many of them, but when you have got grid following, it does involve PLL, for the synchronization purpose. But for here we don't need actually PLL, because it actually produce the frequency and angle reference. So it use like virtual synchronous droop control PSC to create voltage and frequency. And you see that the use cases could be microgrid, off-grid, backup fuel cell. But for this one, either PLL based current control loop And as I said, the function mainly to inject power into the grid, and also like the just synchronize with the current grid, and it's mainly used for gate connector system. Sometimes you also have like some special configuration, like sometimes it could be bidirectional inverter, and this application also getting quite common, mainly if you use like the storage. So you need to charge and the discharge the battery even for fuel cell storage, producing hydrogen, and from hydrogen to again electricity. So we need actually the bidirectional system, and that also can ensure the regenerative operation as well. And also the other technology, we are working in the power electronics, they are also working on the MMC, modular multi-level converter, because it's quite efficient, and as it is modular, it is scalable as well. And when you have got large scale stationary fuel cell, this might be the better solution for that particular application. So anyway, I mean, what type of technology we're gonna use? Again, I mean, as I said, that it depends heavily on the application and I mean their characteristics as well. Now that's more like the technology, but the fuel cell has got particular characteristics, and one of the characteristics of whoever working in the fuel cell, we heavily utilize the polarization curve. I mean here you can see this one, and if you want to produce this curve, I mean you can do this like experiment using electrolyzer, which might have solar module, and then that's like the fuel cell, and then different because at the end you need to measure voltage and current for the fuel cell. So using voltage and current, I mean if we actually draw the characteristic curve, you're gonna get the curve like this. So you see here there are mainly three regions. One is activation polarization region, ohmic polarization region, and then this mass transport polarization region. But when we actually operate that fuel cell, we mostly operate in the ohmic region. So when we do model analysis, you make sure that we operate in the ohmic region. So this three region, I mean definitely there are some involved with there are some losses. So the activation losses, I mean just to activate that fuel cell operation, and as it has got resistance, it does involve some ohmic losses, and it's mostly like resistance dominate, not dominated by induction. So you get mostly linear part. Then you could also have other characteristic in terms like the power density, how much power you are getting per unit area, because we need higher power density, mostly that will make the overall system compact, and this is one of them actually that have got quite potential to have higher density. Also we need to check when the load changes, how the efficiency changes, how is the efficiency at the low load, how the efficiency at the very high load, and definitely the lifetime and durability, that is also quite important, and we need to find the characteristics for different fuel cell technology as well. So I already mentioned, but here if you want to learn more details about those region is given. So again, as I say, this is the over voltage required to overcome the activation energy of the electrochemical reaction, because to start the chemical reaction we need some voltages, that is we consider as a losses in the overall system, and the over voltage is not very high, it's 0.1 to 0.2 volt, and then later due to that resistance, we have got that polarization part, and the cell component that contribute to electric resistance are the, we have got electrolyte, we have got the catalyst layer, the gas diffusion layer, bipolar plates, internal like the contacts, and even the terminal which have also connection. All of them actually contribute that internal resistance. And then there are like the mass transport, like water. So for that also there are some losses, which is mainly model here, but in many applications we neglect that part as well, because that is not actually quite significant. Fuel cell efficiency, I mean again like all other technology, I mean if you measure output and input, you can find efficiency. Normal range like in 40 to 60%, but if you combine CSP, it's gonna be more than 80%. And some of the factors that affect that efficiency is like different fuel cell technology that can actually, alkyne proton exchange member that can affect the efficiency, operating condition, pressures, flow rates that can influence efficiency. The loads, fuel cell may have, slightly lower efficiency when you have got lower output. If you operate like, rated capacity, you might get high efficiency, and also the maintenance and internal energy consumption due to parasitic, that also might affect the efficiency as well. So if you have got like proper maintenance, that might ensure proper operation, and that also can improve efficiency. So you already know that. I'm not gonna. So if you want only individual efficiency, then you can power output, chemical energy input. But if you want to with the heat, then also you need to add heat as a energy output as well. That one showing like efficiency for different fuel cell technology. But if you see that PEM, that quite good. But other also have got efficiency, but in other cases they have got other limitation. So if you compare with other power plant, then you see that fuel cell have got significant compared to internal combustion IC engine based car, coal power plant, gas turbine combined cycle. So you see that in terms of efficiency, fuel with CSP that has got significant like higher efficiency that one. Yeah, so these are the some of the required hour that's need for different application if you use. So that's I already mentioned in the previous slide. So again, just to conclude, the future definitely is like a green hydrogen, and fuel cell, that's a core technology if you want to generate power from hydrogen. We need like further research and development work to improve the efficiency. Some of the different limitation I mentioned for different fuel cell technology. So that also we need maybe further work to address those. And yeah, definitely it's going to be playing a significant role in decarbonizing the transportation sector, industry, and power generation. So I think that's all about your basic understanding about different fuel cell technology, but how we can model it and also analyze with the grid integration. I'm going to be talking in the next lecture. Thanks for your attention.
Thank you, Professor. So we'll have 5 minutes of question session. If you have any questions, yeah, please.
Good afternoon, sir. Sir, is this fuel cell for the, because it's possible to provide the dynamic response, that is the transient response?
Okay, yeah, that's a good question. I mean, so you know that there is still it's not fuel cell, but there are also some generator, you know, already available that can use hydrogen and actually produce electricity. That if we use hydrogen, that definitely that can, you know, provide inertia and other like, you know, ancillary service to the grid. But even like the inverter technology that I mentioned, that if we use that grid forming technology either for fuel cell or even for electrolyzer, because electrolyzer is just a load, right? But even if you control that one as a load, you can actually solve number of problem in the grid. But this is more like a generator. But even with that, if you use like grid forming technology, then later we're going to show that even some of the case study and example that in Australia I know that there is already number of like real project connecting with the grid to see that how grid forming technology from battery, and some of them they are planning from, you know, hydrogen as well to solve that problem. So to answer your question, yes, that's possible, but again, you know, the grid forming is relatively new technology, right? So there are number of research work is going on to improve the control and also like the overall energy management system that, you know, might be able to provide better ancillary service to the grid. But having said that, I mean, when most of the thing is still like, you know, research and development, right? But to employ like in the real, in the massive scale, definitely we need more pilot project to ensure that, I mean, it actually provide the whatever service it's supposed to do that, because, you know, the grid is like a very critical sector. We can't just, I mean, do experiment by connecting any technology which are not matured and, you know, practically ensure that it actually can provide the service it's supposed to do. So definitely, I mean, we need more research, pilot project and demonstration, but actually it's possible.
The fuel cell vehicle itself, I think they are using some battery for the in between the fuel cell and the load, that's a motor.
Well, but for fuel cell, I mean, definitely, I mean, battery is not the I mean, component for, I mean, because it producing electrical energy from hydrogen, right, using fuel cell. So yeah, I mean, battery is definitely, I mean, not important for, you know, for if, again, I mean, if you want to store it like in even like a separate like, you know, device, but I don't think you need it, because if you have got stored hydrogen, right, okay, you can generate from that one. But if you see that, no, I have got, you know, certain amount of energy, hydrogen, like in the car, and we are going very, very long distance, and I don't have any fuel cell station that I can again fill up. But again, I mean, if you want to do that, the cost gonna be very, very high.
Yeah, that is okay. But what I am saying is the fuel cell, because the kickstart, now sometimes the load, because the motor load will be more, that time it can withstand that amount of power?
Yes, that's definitely possible.
Possible, okay. Yeah. And sir, what about these metal hydrides and the fuel cell?
So metal hydride, I mean, in Australia, I mean, we already have like commercially available one, like metal hydride one, just you can put it like in any, but they're quite actually small. You can put it like in your garage and things like that. But there is still problem that the efficiency is actually quite very, very low. So they actually need to improve that efficiency. Also, in terms of cost, that when you buy electricity from your grid, like an operator, or you are getting electricity from your solar, right? So the if you want to get power from fuel cell, the cost has to be comparable. Otherwise, why are you going to pay more money just to buying that technology and putting in your home, right? While you have got option to get electrical energy from other sources. So to answer your question, yes, the technology is available, but in terms of cost, it's not feasible.
Yeah, the compressed this one hydrogen, we can the safe operation will be possible. No?
Yeah, that's possible, but in terms of cost, I'm saying like that in terms of cost, still it's not feasible if you compare with other option.
Okay, thank you.
Sir, one of your slide I observed that there is a MPPT for the efficiency optimizations. So to optimize the efficiency, which parameters we have to consider for that?
So the MPPT, again, I mean to ensure maximum power.
Yes, yes.
So you know that just consider like your rooftop photovoltaic system, right? So the rooftop photovoltaic system, I mean, during the different part of the day, you have got different intensity for the input light, right? So when that condition changes, so you have got voltage and current, right? So if you multiply voltage and current, you're going to get the power.
Yes, yes.
But that, let's say, I mean, you are operating at a particular point at certain condition. But when the condition changes, if you continue to operate at that particular point, you might not be getting maximum output power. So that MPPT, what it does, that considering all the factors, it continuously changes like the operation of that inverter, I mean on the converter, to ensure that for any condition you are getting, it's not maximum efficiency, it's maximum output power.
So sir, the thing is that to extract the maximum power from the fuel cell, we need to focus on the control strategy of the converter side, like a duty cycle or everything similar like this.
Yes.
Okay, thank you.
But we're going to be, again talking about the control and DC-DC inverter. That time maybe you'll be like more clear how you're going to do it. But again you're right. Mostly is the control part. Nothing about the power circuit.
Power circuit.
Yeah.
Okay. Thank you, sir.
Yeah.
Okay. Thank you, Professor, for the talk. And here we are closing lecture 2, and we are exactly 20 minutes late to the schedule. So we will meet again after the lunch here in this room 2:30 p.m. And as we mentioned, we have canteen and mess facilities like 5 to 10 minutes walk from here, and you can avail your lunch there. See you soon.